Hi everyone, and today I'm pleased to present Peter and Nikita, who have done great work to use knowledge graphs and imbuing it with semantic and episodic memory in order to create a continually learning agent that does very, very complex environments. Okay, I wouldn't say very complex, but at least complex environments in the text domain. So I actually met Peter because I saw his paper on archive, and when I read it, it was like, wow, this paper really talks about a lot of very interesting things, and I agree with most of them. So I definitely have to contact him, and that's why he's here today. And Peter he had a PhD in neuroscience, and now he's trying to apply these insights into AI, which is exactly a direction that I'm very interested in. I think there's a lot to learn about the human brain and how we do things efficiently. And if we can imbue some of these guiding principles into our AI systems, they'll be way more better than what we have today. And Nikita is a fourth year undergraduate doing mathematics, and it's amazing how he can write a paper when he's still an undergrad. So yeah, I'll pass the time on to Peter and Nikita. You want to give an introduction to yourselves, and you can begin the presentation as well.
Yeah, thank you for the introduction, John, and thank you for the opportunity to present our work on your channel. I think your channel is great for the agentic stuff, the LLMs, and one of the best I saw on YouTube. So yeah, as John said, my background is neuroscience. And we met Nikita, I think about a year or so ago, maybe a little bit less. And we share the passion for the creating agentic stuff and the uh, the approaches how to improve LLMs for the reasoning and for the performance in the different tasks. So I think I will mainly present our paper, our ideas, and Nikita will come into maybe share his thoughts or maybe some technical details. Well, if you want, you can interrupt me anytime to ask questions or maybe questions in chat, and also Nikita, feel free to make comments on my talk.
Okay.
So okay, yeah. So maybe a little bit background. First, I started to look into the reinforcement learning stuff when I moved to the AI field because it was, well, the closest thing to the neuroscience stuff, the behavioral stuff, all this, the prediction error, dopamine theories, how the animals learn, and so on. My next step was in the free energy principle, as it's more a global theory about how brain works and how to create smart agents that can use model of the world to behave in the environment. But in the last year, when all this hype around GPTs and GPT 3.5 and GPT-4 started, and I think that was the time when the paradigm in the agentic workflows shifted to the LLMs, as they can apply a more general understanding. So if we used reinforcement learning for some policy stuff or some low-level stuff, how to learn some skill and so on, but we also could use reinforcement learning for like model-based reinforcement learning for some reasoning. But language models do this on the much higher level and a much broader level, I think. And also when all this agentic stuff happened, like the papers on generative agents and Voyager, and a lot more followed that. I thought that there is a great field to apply some stuff, some principles from neuroscience to augment the agentic stuff with language models, how to apply some uh, principles to make agents better and better at performing in the different environments. So I will shortly start with. I'm sure that John's audience are very aware of these graphs. It's like the common representation of agentic schemas for language models, and well, I think this was the in the lowest one. This was the
This
first
one,
one and maybe
yeah,
the most famous, yeah.
is Leland Wang's
And
blog on
yeah,
on
Ling
the
Wang's blog, yeah.
on the components of an
And
agent. Yeah.
yeah, the basic architecture for the agent. And then there were some survey papers on the agents also. And all of them basically talk about the same stuff. So we have some agent in the center that is represented by a language model. We have something about planning, we have something about memory, tool using, and so on. Well, the main stuff I think here is how we can improve the agentic behavior and workflows is through, and most papers will actually focus on like the planning stuff here. And I think there's something like here. Um, this one doesn't really talk about planning, but I think the action selection is something like planning also. So all this like chain of thought, tree of thought, and so on, and the more recent stuff about like rumors about Q star for OpenAI, then adding like some tree structure algorithms like A star or Monte Carlo to the language models, all talk about planning. And the second stuff is like the memory. The memory is in every framework. So the memories, I think it's still the weak points of language models, and um, the agents in particular. So our work focused mainly on the memory. So we did some planning also, but it was not like something new or groundbreaking. So our main contribution was actually the memory stuff. But I think that the memory and planning are also not truly separated. So I think there is a very strong connection between memory planning, and Nikita in particular is now thinking about how to connect this stuff, like the memory and planning. So uh, this is, I think it's pretty obvious that to make a good plan, you need to have experience from the past and remember some stuff from the past. So, um, well, I will talk basically about our paper now, and the main contribution was the memory stuff. I'm sorry for this spikes. Sometimes my PowerPoints just when I draw some stuff make the spikes. So the memory for large language models, well, basically now what's the most to used approach is like the RAG. Everybody knows about this, and expanding the context window of language models. So the RAG stuff, I think, is well, I'll talk a little bit about this later, but the expanding of the context doesn't really work that well. So I think I will also take opportunity to talk about our also our recent paper where we created a data set for testing of long context window language models. So it's basically a needle in a haystack, a more complicated needle in a haystack variant. So, and we tested a lot of different approaches, different language models, and also some Mambo stuff, some RAG also. And we show that with the increase of the context window that you feed into the language model, the performance decrease very dramatically. So it's also very important for the agents that interact with the environment. We also show it in our paper. So if there's some like structure thing in the long context, in the context window of a long context of language model, it can actually solve maybe this. But if there is a lot of stuff like observations and actions and some other stuff from the interaction with the environment, it becomes very hard to make sense of all this data for the language model. So this approach doesn't really work well. And the second stuff is RAG, the retrieval augmented generation. So when we store the information in somewhere else in some database and retrieve it to the context of the language model. So this is like the most hype approach right now, but it mostly uses the vector databases like the vector search. So you embed some stuff in the vector and search the similarity and retrieve it. So it has its benefits to the large context window. So you can retrieve the relevant information that is needed, and you don't pollute the context window of a language model. But the native RAG, the basic RAG, also suffers a lot from um, the it's well why we all the ideas in our paper is about that the RAG is not structured in any way. So you just take some stuff that is similar, but there is no like overall model of your memory, no connections in your memory. So the how our brain works, we have a internal like model, and we connect stuff to each other. And RAG is just like some pieces that somewhere in the vector space, and they don't connect to each other in any way. So the idea in our
Sorry, Peter. I want to add that classic RAG is suffer from mistakes of embedder or inaccurates of embedder, because we actually can't represent large or small pieces of text in vector space without lost some meaningful things, some relations, and etc. All the stuff we can handle with knowledge graph. We can form some information structure with explicit connections between entities. But with RAG, we completely can't achieve this level of connectivity and meaningfulness, because our embedders are still very weak indeed.
Yeah.
Yeah, I agree. So we depend on the embedding model, and also we depend on the chunking strategy. We don't know how do we use like 100 tokens or like sentences or like 1,000 tokens and so on to chunk the initial text. Yeah, John, you wanted to say
Yeah,
something?
I just wanted to add something. So this whole slide on memory is very interesting to me. In fact, my entire like 10-year plan, if you know about my other videos, like is actually to create robust enough memory spaces that cover enough abstraction spaces to solve any arbitrary problem. Like I believe that you don't only have one memory, like maybe the summarization. You also have different other kinds of memory, like for details. Like, you know, if a painting, you have a kind of memory to store maybe your pixels, some to store objects, some to store maybe actions. So this kind of different memory spaces is very crucial to solving problems, and you need to select the right ones to solve it. So the two approaches that are presented here, and that are mainly the ones in use right now, retrieval augmented generation, the RAG, suffers from the fact that like it's as what you have already mentioned, it's not very context based. I mean, you sometimes you don't retrieve the right things, and after you retrieve one chunk, you might actually need another chunk, but it's not retrieved as well. So you lose the overall picture. So this is because RAG is typically done over chunks of documents and stuff, which are at the one level of abstraction space, which is at the bottom. Like if you want to get a more overall understanding of the text, using RAG may not help you get that. Okay, unless you take the neighboring chunks and so on. Okay, long context. The problem of long context is that LLMs in general don't really pay attention very well to very long context, as mentioned. And I also faced this in my experiments when I did the abstraction and reasoning corpus. I gave it a very long context with a lot of action spaces, a lot of functions to use. The longer the list of functions, the worse the performance. Okay, you would think that actually you give it more actions for the agent to use, the better, right? Actually, no, the worse. Because the LMs don't actually reason that well when there's a lot of different actions to choose. Okay, they do pattern matching, and if you put too many, they might just give you a wrong action just because it might semantically match and so on. So long context is actually not the real solution to performance systems. The solution is to pick very, very concise context and make it useful and relevant. So I think you'll discuss more about how you did it for this AriGraph. And I think something like this kind of approach is definitely the way ahead to maintain the information in the context, but not flood the agentic system or the LLM with too much information. Yeah, so back to you.
Yeah, sure. I will move to actually our paper. So we decided to use text-based games for our environment. I think that it's a good benchmark because we don't need to actually check the performance of some visual language model or some CNN to extract some information, because mainly even now currently high multimodal models, they're still reason and plan in the text space. There is maybe some improvement in the understanding of the actual world through pictures and videos, but the main reasoning is still in the text domain. So the text-based games and environments are a good benchmark for the LLM reasoning and memory for our task. So we first started from the Zork game. It was the most popular one for the reinforcement learning benchmarks and so on, and maybe the most popular text-based game in general from the 80s, from the when people were still playing like in the console in the DOS console. So it's a pretty large map, and first, what we did was trying to create some knowledge graph of using the existing solutions, like the Neo4j examples for creating knowledge graph from the. So I took the example from Neo4j on how to create a knowledge graph from the Wikipedia and tried to apply it to the Zork game for the navigation task. So I just took an agent with a perfect walkthrough. So just the agent didn't decide the actions. It just followed the provided walkthrough for the game. And I asked it to create a map of this game, and it was pretty decent, I say. So next we could ask it to, for example, how to get from this location to this location, and it would create something like cipher query to find the shortest path between two nodes. Well, and it as I said, it worked pretty decent. It worked okay, but then we tried to apply some planning and action selection from the agent itself and so on. And it turned out this type of games are very hard for the current LLM systems, and there is a lot of logic that is very non-trivial for even for humans, and it needs a lot of try and error actions to perform. So we decided to take a step back and create simpler environments to test our approach. So
just a
what
moment
task?
there.
Yeah,
Actually, I have a question on the previous slide.
yeah,
So
sure.
I just wanted to ask you, what's your opinion of this, like using a cipher query or some query to navigate from one node to another node in a known knowledge graph? Would you consider that navigation from one node to another as a reasoning process, or is it a search process?
I think it depends on the nodes that you want to connect. So if in this task, when there is only locations and you just need to make a path from one location to another, it's pretty simple. You just connect two nodes and find the shortest path. But if there is a huge knowledge graph with different kinds of nodes and connections and type of nodes and so on, if you just make a cipher query to connect to two different nodes, it's not always will be the result you desire. So I think the reasoning process on the knowledge graph, you can of course use some algorithms, some search algorithms, and we also tried in our paper like some A-star to connect some nodes. Well, it didn't quite really work that good for the bigger knowledge graph, but we didn't spend a lot of time on it, so I think it could be also improved. Well, the ideal thing is, I think that if we use language model to make some reasoning on the next step on the knowledge graph. So, well, what's the relevant connections to the task that you are performing? So if you like starting in this node, like select the nodes that you think are relevant to the query or so on. But this stuff could be very expensive also if you have a huge knowledge graph and you need to check all the connections. So I think the ideal thing is try to do both, like some algorithm on the knowledge graph plus the reasoning of the language model to select the best nodes to take. I will.
Sorry, Peter. I also want to add some thoughts about the discussed problem. Uh, Reasoning with LLMs across knowledge graph is obviously good and interesting solution, but I think that adding some labels to nodes and vertices in graph can be another orthogonal solution which can which may be used for cipher query. We can see on reasoning across graph like mm, free thought with LLM or like builded connections with builded in the past connections with cipher query. If we add labels to nodes and vertices, we can use it later without reasoning with LLM, without LLM inference, but still with some additional information to cipher query. I mean this.
I think the
Yes.
main thing that I wanted to ask was, can knowledge graph traversal replace LLM-based reasoning? And I think the answer is yes, if you store it in the right format in your graph. So I think this, I mean, although I am not really a firm believer that we reason through our actions, we are more like pattern matches for humans. This one we can talk about it another time. But at least in order to get from one node to another node, if your reasoning traces are stored in your knowledge graph, then effectively going from one source node to the end node, you actually reason through your decisions all the way because you store the reasoning in this graph. And I think that's the point I wanted to make actually. Like, I don't think large language models are very good reasoners. They are very good pattern matches. If you ask them to reason, it's a hit or miss. Sometimes you get good reasoning, sometimes you don't. But at least constraining it with whatever you store in this knowledge graph, like there's valid traces of reasoning or like sequence of actions, at least I think it can help to solve a little bit of the reasoning or planning problem in that you managed to give some context to the language model to follow. Yeah, so that was my main point there. You can feel free to follow up or we can move on.
Yeah, I agree with you that, well, basically what we're doing with language models with this stuff with RAG and so on is basically constraining them on some stuff. Yeah, so giving them additional context, additional information to work with. So yeah, I agree with you that the and knowledge graph in this case can be a good constrainer in this sense. Yeah, so next I want to quickly address our environment. So what task we decided to do? Oh, the first one was we called it treasure hunt. It's basically finding the treasure in some kind of environment labyrinth. So the player starts in this location in the first one, and there is also a golden locker inside it. And in golden locker is a treasure that the player needs to acquire. But the golden locker is locked, and the key for golden locker are somewhere in the environment in the another locker. And there is also a key one and the instruction that key one opens the white locker. So the task is to like take key one, find the white locker that is here, then take key two, find the next locker that key two unlocks, and so on. So you need to navigate through environment and find the golden locker, the golden key in the end, and return to your start location and acquire the treasure. So this was like the main environment for this treasure hunt. We also had a harder version that is basically just more keys and more rooms. The next environment we created, we called it cleaning. It's like the house with 9 rooms, and in each room there are some stuff. So, and some stuff is placed correctly, and some stuff are out of place. So, for example, a toothbrush on the dining table in dining room, or like the dumbbell on the study table in kids' room. And the agent needs to navigate this environment and locate the things that are out of place, and then place it in the right place. So, for example, it needs to take the toothbrush and move it to the bathroom sink in the bathroom, and it gets a reward for this. And the dumbbell should be in the gym, in the dumbbell stand here. And the last type of environment is cooking. It's actually from the what we use the TextWorld library, and it was like the main benchmark that was created by the authors in the TextWorld environment. So the agent starts somewhere in the environment, and it needs to find the cookbook. And in the cookbook, there is a recipe, like there is some ingredients that you need to acquire, and there's direction what you need to do with the ingredients. And all this stuff, like all the sections, are specific. So, for example, if you need to grill yellow potato, you need to use barbecue for grilling. If you need to fry, you need to use the stove. And dicing and slicing are made with a knife, but you need actually to perform the right action. So, and the hard thing with this environment, if you do the wrong action with for example, you need green bell pepper, and if you use, for example, barbecue to cook the green bell pepper, you lose because you need to fry it. Fry is doing with stove, so there is a lot of nuances and to solve in this environment. Yeah, and also we tried on the hard version when there is more rooms, more ingredients, and so on. So as a baseline, so we used the vector database. It's basically the RAG. Yeah, so we embed our observations in the environment, and we take like top 5 of relevant observation to our current observation and plan, and retrieve it to the language model. We used summary. It's like well, just summarize. We have a summary, and on every step we update the summary with some relevant information. All this done is by language model too. And we also use the full history. It's like the put everything that was in the environment to the context of language model. So we tested like the large context like of GPT-4. Could it solve this with like all the information it receives from the environment?
Oh yeah, by the way, that diagram is a very good description of like multiple abstraction spaces of memory. I know in your experiments you only did like one memory each, like vector DBU agent, summary agent, full history agent. Like but if you combine like all this together with like maybe a knowledge graph, maybe not the full history. I think full history is a bit too overloaded. Like if you give different abstraction spaces to the agent, maybe you get a good performance. So I mean this is a maybe. Yep. So at least this is the line of approach that I'm thinking.
Yeah, it's actually a good idea. Maybe we should update our experience with what if we put all 3. I think this one is definitely not, because it will pollute the language and the context, and it will be very hard. But what if we take like top 3 observation plus summary? I think it could be also a good benchmark baseline. So, well, basically what we did, and our main idea contribution, that we would use a knowledge graph as a memory instead of like these three. And our knowledge graph is, well, not just a knowledge graph. We also suggest that we can use both semantic and episodic memories. Well, what we call semantic memory is basically the triplets extracted from the observations. Like the knife is on the table, and or barbecue is used for grilling and so on. So this is like semantic memory, human memory, the facts that you know from the environment. And episodic memory is our concrete observations. Yeah, so what's our overall memory of some episode of something that's happened with us in our environments. It was like just the observation that the environment provides, but the good example for the semantic and episodic memory is like Paris is a capital of France. It's like semantic fact, and the memory of when you were in Paris, for example, last summer, some specific stuff can be in the episodic one. So our main idea was to connect these two types of memories, and we did it in a way of a hypergraph. So the episodic memory connects the triplets, the semantic stuff. And the dream is to make an agent that can actually travel through its memories, jumping from the semantic facts to the episodic ones, and then back to semantics. For example, the Paris example. For example, I was in Paris last summer, and it's some fact, and there I met some guy at the conference. It's also some fact, and I remember that we sat in some cafe and talked about some ML stuff. It will be episodic memory, and then you remember some fact from this conversation that could be semantic memory that will lead to another episodic memory, and so on. So we didn't actually implement all this jumping in our paper, but I think it was like the first step to something like this. So here,
Just curious, is this jumping between memories part, like from semantic to episodic and stuff? Is this inspired from neuroscience? Like, do we have a similar phenomena in our heads as well?
yeah, sure. That's how we're thinking. Yeah, so we use some facts stored in our cortex, like in the semantic, and also we use some these facts can trigger some episodic memories from that use hippocampus to construct this episodic memory from different parts of our brain, and so we can as I said, jump from one thing to another, and that's how our imagination maybe and our reasoning process also works.
Yeah, this one, I have a follow-up question on this, if you don't mind to entertain this. This is not really related to your paper, but for episodic memory in humans, like we can similarly compress a very long event into a very short snippet. And like we can think about, at this place I did this activity. Like you can literally flash back in within a second. Because like the way it's stored right now, you store the entire observation and so on. Like, how do you think the brain does this compression? And also the second thing is we may not trigger any flashbacks consciously. Like, so how do we know when to activate this episodic memory and when not to? Like, or is it always activated, just that we are not conscious of it sometimes? Yeah.
Yeah, that's a very good question, and the true answer is I don't actually know. So I thought about this, but I didn't came to the solution I think is right. So yeah, in our brain, sometimes we remember stuff, sometimes we don't. So for the agent, what will be the right implementation for the agent? What's important and what's not? I think that maybe how we do it, how our brain does it, yeah, maybe it's not the optimal way. So we can sometimes forget the stuff that is really crucial, and sometimes remember the stuff that really is not necessary for the current problem, and so on. So we really need to think about it, how to implement this this process of navigating through memory for the agents to optimize its its behavior and the problem solving capabilities. If we're talking about some like proxy for human behavior, like we need some agent just to talk about stuff and maybe be creative or something. It's the different thing. But if we're talking about the agent that needs to like solve the specific task and retrieve only the relevant information, that can be another thing. But I think, yeah, you raised a very good question and problem. So how to decide what's needed and what's not.
Yeah, I think
So
this
I
is a
think
problem that will take a few years to solve. We will need to experiment with different architectures because the truth is neuroscience is not advanced enough for us to know all the mechanics yet. We only know some general things. So like I'm even thinking that stuff like episodic memory may actually be of a different form of rather than just combining all the semantic memory triplets together. It might actually be another abstraction space that is separate altogether from the semantic memory, or it could be combined like over here. So I think we don't have to fix it to make it like a superset of semantic memory. It could just be totally different. Like, with all the like video processing models, you could jolly well be, we just query the video and then you get the answer. Like you don't really need the facts in the video per se, it's extracted out in that semantic space of a video or an image. Yeah.
yeah, but the thing is, you can actually trigger the episodic memories from the semantic. So in our work, in our paper we show that actually applying the episodic memories plus the semantic memories actually helps the language model to reason. So if you just have some facts, it can make a mistake. If you just have some episodic memories, it can also make a mistake. But if you combine the prompt, the facts plus the observation from where the facts were extracted, it's dramatically increased the chance of language model to make a right decision. Well, maybe when there's like some GPT-5 or so on, it's not necessary. You can just provide a simple fact and it will catch it. But right now, it helps a lot.
I understand. Here we are talking about how to choose the right like triplets to present to the user or present to the agent using both the semantic, which is the more specific memory, and the episodic, which blankets all the semantic memory that happens at a particular time instance. So this is the work that you are doing now. The stuff that I was talking on about actually is not related to this work. It's more like, maybe episodic memory could be represented by a different form, semantic memory by a different form. Maybe they are not linked, but they are linked by maybe some common substrate like language. Like through language, you might trigger different episodic memory, you might trigger different semantic memory. And it need not be a superset like what is done here. So I'm just giving like food for thought here. Yeah. So this is not what you have
Okay.
implemented in this paper, but this is something that I was thinking about.
Okay, I get it. So I think we need to
Yeah, I think
speed up a
we
little
can.
bit.
Yeah,
Yeah.
but before you speed up, one last question from me, and then you can have the rest.
Okay.
Over here, just to let everyone else know, like, when you talk about RAG, are you doing RAG over the triplets in the knowledge graph? Yeah, that's the question that I wanted to ask.
Well, do you asking about this baseline or
Yes,
you're asking
baseline,
about?
baseline.
No, the baseline is the reg for the observations. So we store the embedding of each observation. So it's basically this one, and retrieve the full observation. We also use reg in our approach for the triplet extraction. I will talk about it a little bit later.
So actually, rag over the right abstraction space can be quite important. Like in AriGraph, you rag over the triplets, right? So that was more performant than pure rag over the observation space.
Yeah.
Cool. All right. I won't interrupt you. You can continue.
So yeah, here are results for our study. So our approach outperformed all other memories. It's like the median for all the environments and all the trials. We also benchmarked for the human players. So the top human players could solve all the tasks, but the average performance of human players was like a little bit better than all other baselines. So we basically have beaten the average human performance on the text-based games. But I wouldn't say that humans are dumb. Probably the text-based games are not like very easy to solve for a human. So if it was like some pictures and observations, it will be easier. So you need to read a lot of text and remember a lot of information actually to solve this task. So only if you apply a lot of attention and precision, yeah, like these guys, you can solve this. So, well, I think I will skip this part. The overall architecture of our agent. So we have what we call working memory. It's basically what's in the context of the language model. So we have observation from the environment. We have a goal to fulfill, like find the treasure or clean the house. We have a current plan, and the memory is represented by the semantic memories in the form of the triplets. The episodic memories, it's like the top extracted observations from the past, and we also have like something like a short-term memory. It's recent actions and observations, like 5 recent observations and actions, like you were there, you did this, then it led to this, and then you did this, and so on. They're our main agentic well, the core of our agent is planning and decision making. We decided to split this in 2 parts. The planning is, well, basically the LLM receives all information from the working memory, and we ask it to generate a plan. Yeah, and the plan consists of sub goals, like sub goal 1, sub goal 2, sub goal 3, and reasons for these sub goals. So it's like we ask it to generate a JSON file with a sub goal, reason, sub goal, reason, and so on. Well, we also tried to well, not tried, we actually did it to ask it to generate emotions for the current state. Well, we didn't make some statistical or actual benchmarks if it's numerical studies if it helps, but from our observation that including emotions actually helps the agent not to, for example, stuck in some action loop. For example, if it does the same action over and over again, and then you introduce something like your emotion about this, it can say that I'm frustrated, and this moves it to try something else, or it then writes, I'm frustrated about this, so I don't want to try this anymore. I will do some other stuff. And the second one, the second module is a decision-making module. We could actually, and we tried it to make it like the same stuff. We just make some other entries in the JSON file for the action you want to take, and for the reason for the action. But it worked poorly. So dividing the agent to the planning decision-making model actually makes a difference, mainly because I think it separates the tasks for the language model, and it can focus on some specific tasks. So when we ask it to make a plan, it makes like a specific plan. When we ask it to make a decision, it makes a more a better decision at this stage. So this decision-making model actually takes all this the same information, but it outputs an action and the reason for action. It's basically something like a React when you state why you want to make an action, and then you just output the action from the available actions. So, and our main contribution is the memory model. We call it AriGraph or modeling. Yeah. So it's the basically knowledge graph that is updated at every step of the environment, and it provides the semantic memories and later the episodic memories also for the planning and decision-making agent. So the structure of our memory, as I said before, it's like a knowledge graph with triplets that is connected with HyperEdge as episodic memory. So, for example, this is like triplets from the observation of the kitchen. So the agent receives observation that you are in the kitchen, there is a fridge, there is a table, there is something else, you see this, and this. So we take the triplets from this observation and also store the observation itself and the triplets that we extracted from this observation connected to this observation. So this is basically how we extract triplets. It's done by the language model, just the prompt that we wrote for our environment. Yeah. So from the observation, we extract triplets in the specific form. Then we also update our memory. So if, for example, you enter a kitchen, you see that there is a knife on the table, the language model extracts the triplet, the knife is on the table. Then if you take a knife from the table, you need to update your knowledge graph with relevant information. So you need to replace the triplets. Oh, here the example is toy storage cabinet is open, toy storage cabinet is closed, and so on. So we basically extract the entities from the new triplets that the language model generated, and we search for these entities in our current knowledge graph, and we extract some subgraphs, and then we feed this subgraph plus the new triplets to the LLM and ask it to make a list of triplets that is outdated and that you need to replace. And the episodic memory, as I said, it connects the different triplets to the whole episodic observation in our environment. So, for example, there's like a picture, or in our case, it's just text describing this environment, and these are the triplets that we extracted from this observation, and we connect it to each other. So the retrieve process that we use is the following. We have observation, for example, that the agent receives from the environment. Then we ask a language model to extract some relevant items from this observation. Here it's just a list, but we in our code we actually ask it to make a dictionary where each key is in some item, and then there is some relevant number to the current goal, to the current plan of the agent. How important is this item from this observation, and the plan also to the current goals. And then we search. Basically, we make a RAG. So we use an embedding model to embed this stuff, and we also embed our triplets and entities from our knowledge graph. We search for the top relevant entities from the knowledge graph to the extracted ones, and then we make a search through the graph, like BFS and breadth first search for the depths of the importance that LLM thought that this entity is, how much this is important. So, for example, if apple is 2, we will find some relevant triplets to the apple. Then we'll make and we find the entities from these triplets and make and find the for example, I don't know, apple apple is on the table, yeah. So we'll find the apple, the table, and we will search for the connected nodes in the knowledge graph for the apple and the table, and so on. And so we continue this loop until the depths of all these entities are extracted in the form of subgraphs, and then we feed this as a semantic memory to the language models. And then we also, to take the extracted triplets from all this search, and we search for the episodic memories that is the most amount of triplets has the most amount of triplets in it. So as I said before, for example, this is the observation, and we extracted like three of these triplets that are relevant to our current plan and goal. And from another observation, we extracted like 1. So we take the top like 2 or 3 observations that has the most amount of triplets that was initially extracted from them, to also take this observation and put it in the context of the language model. So basically this we end up with the triplets as a semantic memory, yeah, and observations as an episodic memory. So here I can provide some example how it can be done. For example, if we ask an agent to follow the recipe to cook a meal, for example, we can extract that. We can find the entity recipe that is important for this query. Then we can find that recipe contains green bell pepper and yellow potato. Then we can move to the yellow potato, for example, need to be grilled, then we can connect the grill and grilling stuff by embeddings, and because every step in our semantic search is through embeddings, then we can see that barbecue is used for grilling, that you need to use barbecue, and then we can extract that backyard contains barbecue. So this chain provides the information for the agent just by the query of that you need to follow the recipe. It can extract all relevant information. That's what it needs to gather, and what it needs to do with it, and where can it find it. And also we can extract the relevant observation, for example, the recipe itself. So this red stuff is the representation of the observation of the recipe that I showed in the beginning, for example, this one. So the agent will also receive triplets plus this thing. So if there is some maybe directions or some specific stuff that is not extracted by the triplets, it can also use this information too. So yeah, I think this is also an interesting stuff. We didn't provide this graph in the paper, but this is the algorithms that we use aside from language model, how we navigate graph and how we do the exploration. So this graph, actually, I did it to showcase that language models are still bad at the navigation in some spaces. The task was I just gave it a graph, the form of triplets in the task that's similar to ours, like the room B is north to room C, room D is to the east of room B, and so on. So this the x-axis shows the number of connections in the rooms. So I asked the GPT-4 to make a path between several rooms. So this is like 2 means that you only need to make 2 steps, 3 steps, and so on. And the score is like did it how many times it succeed out of, I think, 20 runs. So it shows that when there is a for example, if there is only one connection, it's room B is to the east of room A. The GPT-4 can solve it 100%. Yeah, so it understands the relation between south, north, and so on. But when there is when you need to make several steps, well, the chain of thought helps, but not for it doesn't solve the problem, and you see that the performance drops dramatically. So in our task, when we have quite a big environment and we need to navigate from one direction to the other, we couldn't just provide the triplets to the language model and pray for it to find the path. So we actually made navigation knowledge graph. We took the locations, so the entities that had location tag on it, and just use Nikita, I think we used BFS too. So you can use different algorithms like A-star and something like this, but our environments were not like huge, so I think we used just BFS to find
Yes,
the
just
shortest path.
BFS,
Yeah.
because we haven't thousands or millions number of rooms. We have tens or hundreds rooms, and so we can use just BFS to find the shortest path. That's quite fast.
Yeah, so basically, if we have like a lot of some nodes, yes, we need to find the path from here to here. We make it as a, well, basically something like a function call, but we did it in the form of action. So we just provide the language model with additional actions. Move to room X, for example. If you're starting in room A, you have possibilities of choosing action, move to room, for example, room C, and it performs the BFS on the allocations
So that's
on the
interesting.
knowledge graph.
So you provide the macro action like move to C from A, and when the LM chooses move to C, you will execute all the in-between steps on behalf of the agent.
Yeah. So basically, yeah,
Oh,
we
nice.
we teleported to the, well, not teleported. We just perform we give it the
I mean,
action sequence,
technically,
action sequence that it needs to perform to move to the right location. Yeah.
yeah, technically in effect you could teleport, but I mean in the text world you just perform the right sequence of actions because
Yeah.
this is a deterministic world, right? So you could just perform the exact same sequence. Of course, when we move to non-deterministic, then we will need to change this architecture a little. But the idea of abstracting the action space from like one single step to many steps at one time, I like this idea because it helps a lot with planning. Like it helps if you can plan at a more macro level and have something to help to decompose into the smaller steps. So your top level planner doesn't need to care too much about the details. One question about your navigation graphs. Do you put any KG information, knowledge graph information when you ran this experiment? Is this just purely based on the textual observation and running GPT-4 on it? Or the graph on the left?
So basically, it's the input was in a formation knowledge graph. Yeah. So it were triplets,
Oh,
like
wow. So
room
even with
C is south of room B, room B
I
is
see, I
north
see.
of room D, and so on.
So even with the triplets, it performed poorly.
Yeah. So it was only the relevant information, so no distractions. And as you see on the like the five steps, it's just couldn't perform any success in this task.
Yeah, actually in the TaskGen paper, I also did a maze navigation environment, and I realized similar things. If I ask the LM to perform like move up, move up, move up singly, right? It performs worse than if I say move up 5 times. And then I just do the 5 times for the agent. Then move right 10 times. If the agent is able to do a bit more macro stuff, the plan length from 100 is going down to 3 or 4, and that makes the whole plan more reliable. Yeah, and one other thing I realized that makes it even more reliable is that if you generate a list of steps already and you just execute the steps one by one until failure, this guaranteed sequence of steps helps to improve the reliability so much that it got 100% solve rate on my environment. So before giving this list of steps, it was like maybe 50% solve rate. Yeah, so having a constraint on the next action to do could be helpful for large language models who tend to, because you can reason, I need to go forward. Then the next reasoning it gives, I need to go backward. Then, you can go forward, backward, indefinitely. So I think this might be happening for this environment as well. Like, that's why I say LLMs don't really reason that well. They pattern match. So in order to solve this kind of navigation stuff, it's best offloaded to a rule-based planner. Like in this case, your depth first search or whatever. Then you can offload some of the cognitive abilities by using already a predeterministic way of navigating. Yeah, and I think that's what we need to do because if you use LM for navigation, it's quite bad.
Yeah. but maybe it can be solved by introducing like the modalities and the understanding of the world, what is south, what is north, but I'm not sure. So it needs to be a lot of experiments still needs to be done. So now I agree
This, by
with
the
you.
way,
Yes.
also shows how tough the TextWorld environment is. I tried it myself. It was extremely frustrating for myself, a human, to play. Like even the simplest environment, I think took 20 to 30 actions, which is actually very, very tough. Like this is not even considering navigation. Like navigation, you need to remember the whole map in your head, which is also very tough. Yeah, so I think this highlights how difficult the TextWorld is for LLM agents.
Yeah, you actually need to draw the map to to navigate it. So it's very hard to remember all the connections in your head. Yeah. Yeah. So we also did the exploration algorithm. We struggled first with the language model of the agent doing the same stuff over and over again, like moving from one room to another and then back, as you said. So moving between two rooms again and again. So we needed some kind of exploration. Well, we thought of different types. For example, something like reinforcement learning, trying all different stuff, all different actions. We still think that it could be possibly the interesting way and approach to the exploration, but we actually wanted to make a zero-shot agent for our paper that doesn't try every single action. Actually, reasons to make the best possible one. So our exploration was based on also the knowledge graph. So we took also the locations, the nodes with a location tag, and we searched for all the triplets that contain something about exits. So because in the TextWorld environment, the observation provides the exit. So for example, you in the kitchen, there's an exit to the west, there is an exit to the east, something like this. And this is all extracted in the form of triplets for our knowledge graph. So for example, the kitchen location has two triplets that it has exit to the east and it has exit to the west. And what we did, we search for each location and then search for each exit from this location, and then we see if there are also the triplets that connect this location to the other location. So if, for example, the kitchen has exit to the west, and there is also a triplet that, for example, the living room is to the west of the kitchen, then we think that this exit was also already explored because there is information in the knowledge graph which rooms connect to the kitchen from the west. And so we go through all locations, and we provide the language model as a form of memory, also the exits that I didn't explore yet. So you could say that it's something here also, exploration, yeah. And we also it can also the pollute the the context window of the model. So we have like a sub agent, sub LLM that decides if you need exploration in this situation. So it receives its plan, and if there is something like find something, locate something, and so on in the plan, that then we turn on this exploration stuff, and that provides the information about and explore exits to the language model. And if there is a stuff like do some stuff like open something or cut something or prepare something, you don't need this exploration. It will not be provided to the language model. So here are our results on the different environments. We did some ablation studies for our architecture with episodic memory and exploration. So as you see, the benchmarks, the summary, rec, and full history are not performing too well. On different tasks, for example, the cleaning full history just doesn't work at all, and the treasure hunt, it works a little bit. And I think the interesting stuff is the ablation studies. For example, in the cooking one, the episodic memory was very helpful. So without episodic memory, the performance dropped significantly. It was mainly because all this information about what you need to do with specific ingredients like grill, fry, barbecues for grilling, and so on. So if you provide the concrete instructions from the episodic stuff plus the semantic triplets, the performance is much better. But for example, in the cleaning task, the episodic memory, like the full one, actually a little bit decreased the performance. It was funny because and the cleaning environment, you take some stuff that is out of place in the environment and you need to place it back where it belongs. But if you provide episodic memories, for example, the dirty plates was on the bed, yeah, and the agent take this dirty plate to then locate a dishwasher to place it in. But we also provide the episodic memories, the relevant episodic memories of where the agent found the dirty plate. So that basically it enters the room, it sees the dirty plates on the table, and that's the episodic memories. And sometimes these episodic memories are actually retrieved, and the agent decided, well, if I found the dirty plates on the bed, it's probably where it belongs in the first place. So it decided that I don't need to find a dishwasher, I just need to put it back. So in this task, the episodic memory sometimes actually decrease the performance. And I think that the dynamics is also very interesting to see. So this one, it's for the without exploration ablation study. So we see that the agent can actually solve the environment without exploration, but it takes far more steps to do so. So the full red line is our agent. The dotted one is without episodic memory, and these slashes is without exploration. So there is also a result for the hard environments. I think I will show the dynamics there, more interesting. The hard environments, they're even harder for the baseline, so they score far less on the hard environments when there is more actions to do, more rooms, more ingredients, more keys, and so on. And our agent shows that it can solve it without real problems compared to the more easier ones. And so the episodic memory is also very helpful. The harder the environment is, the more contribution the episodic memory provides also. Yeah, and here's the results for the human benchmarks on the treasure hunt cleaning.
The Llama 3 is really not that good.
Yeah, Llama 3 is not that great. So yeah, by the way, we used the GPT-4 Turbo preview because we found out that it has the best planning capabilities out of all GPT-4 models. Yeah, and
I'm quite
Llama
curious
3.
how the new Llama will perform, the Llama 3.5 405B. I wonder if it's
Yeah,
better than GPT-4 or like worse. My suspicion is that it might be a little worse because I think the training data set for GPTs is probably much wider than what Meta use. So in terms of generalizability, Llama 3 is probably, or Llama 3.1 is probably not as generalizable as GPTs. At least this is my opinion.
yeah, I think so. I actually heard that Llama 3.1 is worse than the Llama 3.
I mean, for TaskGen, it is.
The
It doesn't generate JSON that well.
8B and SetCTB, yeah. So I'm curious what's the 5 billion parameter can do. I'm not sure if we can, Nikita, can we run the 405 billion parameters on our cloud, on our GPUs? Do we have enough GPUs to run it?
Probably we can. We have total about 600 gigabytes of GPU memory, and so in floating point 0.16 we can run models up to up to 300 billion parameters. Yeah.
I think yeah, we'll try the new Llama, but uh, I think that the Llama at least it's okay for the triplet extraction and all the other stuff that we do in our framework. It's just its planning capabilities. Well, the bottleneck is planning capabilities of the model and the decision making. So even GPT-4 the and GPT-4 all uh, performed worse than GPT Turbo Preview in the planning stuff. So, but yeah, it will be interesting to run Llama also. So this is dynamics of the human benchmarks and Llama. But for example, in cooking task, the Llama still performed better than the average human baseline. So we found out that the humans like really, if you're not like 100% concentrated on the task, you will still make a lot of mistakes. Maybe it's like the specific of this task because you can basically fry or grill stuff on stove in real life. So humans decide, okay, I will just grill some sausage on the stove, but the gaming task requires you actually to do it on barbecue. So that's why all
Actually,
the
this is an
mistakes.
interesting finding. When there was an experiment that was done on Atari games, or they tried to simulate a game whereby like you need to climb ladders and avoid obstacles. And generally humans do quite well on that task, like zero shot. But the moment they morph the ladders into blue color squares or green color squares,
I remember this one. Yeah, it was
yeah,
impossible. Yeah, to
right.
humans and reinforcement learning some
And the AI
algorithm
could
did
solve it,
it
RL
the
could solve
same.
it, yeah. So it means that actually the way humans solve, we don't actually plan a lot in some sense. We actually more or less pattern match to the world. And it's just somehow that the Atari games matches our world quite well. That's why it's easy for us to play. Or not easy, but it's more manageable to understand. Like for this cooking environment, I also had my hand at it in TextWorld. Extremely tough to understand. The ingredients are all over the place. You don't even know where to cook. You need to find the place to cook. It's not realistic. Like in real life, when you cook, everything's at the kitchen. Done.
Yeah.
But in this TextWorld, it's like doesn't match real life, and I can understand why humans do so badly at it. Yeah. So it also shows the difference between AI and humans. Humans are more like we actually learn the environment quite well, while for the AI side, even your environment is not that well matched, like it's still able to learn. And I suspect it's a lot to do with the knowledge graph, because if you take away the knowledge graph, but maybe the performance will be worse than humans for the LLMs. Yeah, because it's really very hard to pattern match without this kind of association between memories and so on.
Yeah, but language models are closer to humans closer to the humans that
They are closer, but
our
the memory
algorithms.
structure here is a little more like you can remember more with AI compared to humans. Like I think like the amount of context that these models are taking in is way more than what a human would be able to take in.
Yeah, sure. But there were similar benchmarks for language models in the TextWorld environment when for example, the LLM can solve some blocks world, like put this block on this block and so on, but then you change the blocks for some random random letters and so on, and the actions for also for some random representations, and LLMs fell miserably. So because they are trained on the text and the human data, and they also have some biases for our representation of the world. So it differs from the reinforcement learning when you just learn from pixels without some any previous knowledge.
Understand. Actually, I just thought of another reason why LLMs could do better than humans in cooking. Because you're right, LLMs actually and humans are quite similar in the sense they do semantic matching. In this case, for the cooking, did you imbue the macro action thing? Like basically you give a macro action if two nodes are connected, like you give like go from room A to room C. Do you give this action to this agent here for the
Yeah,
human?
in every environment, every agent, well, our agent with a knowledge graph had these actions, like
Yeah.
move
So
from one to another.
I suspect not just the memory can be longer than humans. I suspect that this macro actions thing could already help to improve the success rate dramatically. Like for humans, if you give humans like a cheat code saying that, hey, get the stove from room A back to room B, and then you do all the not stove, you can't shift the stove. Get the apple from room A and go back to room B. I think this would also help to improve the human success rate. Like if you have this kind of like based on what you have seen so far, these are the suggested actions to complete the task based on your knowledge graph. Yeah, I do think this might improve the human solve rate.
Yeah, but we also told humans to like create write down the map of the environment, so they wouldn't need
No, but right
to store
down and
to
planning is
store.
different. You see. If you do the
Yeah,
macro action thing, you are also doing the plan for the human.
yeah, but when you have the map of the environment in front of your eyes, it's quite easy to make the plan on the navigation stuff, how to move from one location to another. Um, the most mistakes for humans were for the wrong actions performed for the different ingredients. That's why this human all line is so low, and the guys that really solved it, it took longer time than the agent, but still they explored like all the environments, looked at different things, but they paid attention to the instructions, and maybe I wrote down the instructions and succeeded in the end. Maybe some people were just lazy to to do all this stuff. So
Yeah, they gave up halfway, is it?
yeah.
Cool.
Yeah. So I think we're out of time. There's some potential applications for our work. And, also, we compared to the previous reinforcement learning baselines, and we showed that on the cooking task, we show our approach is solves it better than the reinforcement learning ones, but we don't emphasize it too much because there were some differences in how reinforcement learning does it, because it's like thousands, hundreds of thousands iterations, and versus the one-shot tries for our agent, but we also provide some instructions that are relevant to language model, to our agent and our LLM baselines, compared to just the brute force reinforcement learning approach. So it's speculative about how you compare the reinforcement learning to the language models. Yeah, I think that's it.
Yeah. Could we end on the the knowledge graph slide with the episodic and semantic? Because I think that one is quite interesting to talk about.
Sure.
Thanks so much, Peter and Nikita, for presenting this. And I do think this is a promising architecture in the form that it can help with the planning by extracting relevant snippets of the plan. I mean, you also give macro actions to the agent based on this knowledge graph that the triplets that you extracted based on semantic matching and episodic memory matching and form a coherent whole. So this idea of extracting relevant information and feeding to the knowledge graph, feeding to the LM, I think this is a very important approach. And for TextWorld environments, using knowledge graph is a promising way to solve it. So yeah, thanks so much for sharing this. Actually, there's a lot more interesting details about how they choose the knowledge graph nodes, how they extract the knowledge graph with a LM prompt. All these are in the paper. You encouraged to read it. And they also have a GitHub for AriGraph. Yeah. So yeah, I like maybe we spend about 15 minutes if you're okay to like just take any questions or discussion here.
Yeah,
You're
sure.
okay?
Yes, it's
Yep.
okay.
All right. So yeah. Do anyone has any questions? Like
Yeah, so hi, this is Sharno. So I agree with John. Like this is a very excellent way of representing semantic and episodic memories in knowledge graphs. But I just wanted to know, like, let's say it's a dynamic environment. So is there any way to capture the temporal changes in the environment? So for example, like the agent, let's say, suppose sees like the apples are there in the tree, and in some later moment the agent sees like some of the apples fell down from the tree. So is there any way to capture these temporal changes within the episodic memory, or just it captures when only the current state?
Yeah, thank you for the question. We actually didn't implement the timing, the temporal things for the knowledge for the graph and for memory system, but it's one of the directions that we're excited to
Okay.
explore. Yeah, the temporal information is very important. So maybe we have some like temporal axis like this for the how the episodic memory moved forward, and so each node also have its like meta information about when it happened and so on. So it wasn't that important for our environments to solve them, but you are very right that it's for the more
Yeah,
general
it's going to be
purpose.
yeah, it's going to be quite helpful for dynamic environments, like where we can keep a history of the temporal changes. And like I was also thinking in this direction, like how to handle the dynamic environments, like how to capture the temporal changes in the environment. But it seems like we have to keep a short horizon history. Like we cannot keep a indefinite horizon, like where we'll be keeping all the histories, like how the environment changes for infinite amount of time. So that is one decision like we need to take while implementing. So I was thinking, probably I didn't have the answer yet. So just wanted to know your thoughts. Like, is there any way like how to keep a check on the horizon, like how much history will be kept?
Yeah, I don't have the specific answer yet. So also, I think we need to try the different stuff and see what sticks. Yeah.
Right. And there is another thing that you talked about. Like you talked about emotions. Like, are you somehow deriving the emotions from the memory, or you're keeping it, or it's just an idea?
No, it's just we have actually a group in our institute that is working on the emotion stuff, and we just try to implement some very simple thing in our framework. Just when the planning and the LLM decides what's its next action and what's the plan, it also writes down the emotion based on the previous actions and observations. So sometimes it can be quite beneficial just as a context to the language model of what it thinks its
Yeah,
emotional
exactly.
state is. Yeah. So no, we didn't store it in any way in the knowledge graph. It's uh, just a thing for the current state. So what do I feel now? I think it will can be also interesting to take these emotions and apply it to the observations, to the past observation, to the memory and story, also as some metadata for the for its memories. So what was the good memory, what was the bad memory, what I liked, what I didn't like, and so on.
So actually the
Exactly.
emotion part is implemented, but it's not used, right, to filter the memories yet.
Yeah, we implemented it. So all our results is with this emotions stuff, but we didn't make some like statistical ablations and so on if it really helps or not. We well, just looking at the results, sometimes we thought that it helps, so it actually didn't hurt, so we left it in our planning framework.
Yeah, I actually really like this idea of emotions, like the example that you talked about. Sometimes the agent stuck in doing the same actions on and on. So I really faced this problem, like while I was solving the science world and another environment. So in that case, like if the agent gets frustrated, I mean that specific more emotion is triggered, then probably it will help the agent to get out of this loop. And I think like emotions helps us, like us as humans, helps us in motivations, in driving the motivations. So in some way we can also control the exploration using emotions. Like if we're able to identify other emotions like fear, or maybe joy, or maybe sadness, then somehow like these emotions can be combined in some way to drive the exploration. And yeah, I think it will be a very much good application. uh,
Yeah, well, basically neuroscience framework, the emotion, it's what drives the learning in many cases. So the feedback, the reward prediction errors is what generates the emotion. So if you do some stuff and it's beneficial, you have a positive emotion, and that promotes learning, or some other, maybe some actions in the same direction. So yeah, I think the incorporating emotions can be very interesting, huge stuff to increase the performance of the agents and maybe exploration in your case. Another example that helped in our case was like the agent sees the locker, for example, that it has the key for, and the emotion it writes down is I'm excited to open this locker because I have a key and I have a for example, my task is to find other keys in open locker, something like this. So I'm very excited to do this next action. And it sometimes actually helps, because without this emotion it can miss this locker. So it sees this locker, but it doesn't open it for some reason, even if there is some relevant memories. And with a positive emotion that I'm very excited to do this stuff, there are more chances that it actually performs the right action to open the locker.
Exactly right. So it's somewhere like it also modulates our objective, and it modulates our resource allocation, like where we should focus most, and it also drives our attention in some way. Like if you're bored on something, probably we like try out something else. And if you're the example that you have given, if you're excited about something, then you'll put more effort on doing that. I mean, put more resources on doing that. So yeah, it's a very important factor.
Yeah.
I like this discussion a lot. In fact, I think emotions is a way to help us to filter the vast search space of memories we have. So this actually is also used in the generative agents paper, the interactive simulacra, where they simulated 25 people in a sandbox environment. The emotions kind of guide which memories to retrieve based on, like, is it surprising? Is it, I mean, mainly surprisal, like from mundane to surprisal. So this, I think, helps us a lot. Like, we don't remember a whole lecture worth of materials in our head, because it can be quite boring, right? But if, let's say, you hurt your foot on one of the tables, you're going to remember that table for life. So you won't get,
Yeah,
yeah.
sure.
So I think this helps us guide a lot with how things are stored and retrieved. Like, you really place a lot more emphasis on high emotional memories. I just wanted to ask a follow-up question, not related to emotions, but more of a dynamic state changes in the knowledge graph. So let's say, look at this diagram here. In observation 3, my garden contains a red pepper. All right. What if in some future step I took the red pepper and put it in my inventory? Like, how would you update the knowledge graph if I were to do that?
We just we delete this triplet, so this connection is deleted, and we create another one that red paper is in inventory.
I see. Do you maintain a separate global variable for inventory, like to store all the stuff you have right now? And like, yeah, so, or is it all in
Well,
graph?
yeah, the inventory part is it's always in the observation. So it's like the part of the observations. It's like
I see.
you are in the kitchen, and here is your inventory. So it's also in the knowledge graph. So we have a note of inventory that some stuff is in inventory, but we found out that it's a crucial part of this task. So we also provide it into
into the
into
other parts of
the
the context, right?
overall observation. Yeah, and if you play its default settings, you can make an action and the command inventory, and it will provide you with your current inventory. But for the language model, we decided to make it automatically appear in each observation.
Yeah, it's very important. And also which room you are in. Those global variables are very important for your decisions. And also like what are the available actions based on the items you have.
Yeah. So the location is also the part of the observations, like where you're in now, kitchen, garden, and so on. And so we also provide it with the actions. First, we actually tried to uh, make a decision based on without providing the actions from the available actions that can be performed, just like what would you do in this situation? But it's uh, it still needs some in between parser that the decision that LLM want to make to map it to the action. So we decided just to feed the actions in the first place to the language model.
Very nice. Then actually my last question for today is basically like, right now this whole environment is deterministic. It's like you move left or you go west, you go to this room. You go right, you go another room, right? Or you pick up an item, it's definitely going to your inventory. Like
Yeah.
if let's say the environment was a little more stochastic in the sense that if you do an action, maybe you grill the sausage, the sausage need not be cooked, maybe the sausage might be overcooked, then you might need to cook again, right? Like, how do you think you can model this inside this knowledge graph? Because like it would be like, okay, I'll just end the question here. If you can answer this part first.
Well, it's definitely will be bigger. So the for example, if you said that we overcooked the sausage, yeah, we will need to make an additional note that like it's overcooked, and there will be a lot more different states that we need to model, and it's probably will be a burden on all the retrieve mechanisms and all the knowledge graph algorithms that we use and so on. So we didn't try the harder one. So then the hardest one we tried was the hard ones examples of our environment when there just was more stuff to do. But we actually want to try with visual environments like the habitat, where you can extract a lot of different stuff, and the things may change in different directions. So it's definitely one of our ways to move forward. So I don't really have an answer for how it will be done. I think it's we'll decide it on the go for the specific tasks.
Yeah, thanks. I think solving this problem is very important because if we have an environment that is a little different from each time you do some action, you may not get the right result. I think that's more realistic for real world environments where sometimes you do actions mainly not just because the environment is stochastic. Environment might be deterministic, but because there are many different actors, you do the same action. Maybe you buy stocks. Sometimes you win, sometimes you lose, right? Money. So this really, it depends on the other actors around us. And we cannot model their minds. We have to treat that as a random variable. And that means the agent needs to plan well in this dynamic environments that not only changes over time, but the agent may not even know that it has changed until it does the right action. So I mean, one way to model this in TextWorld is that like if you do a particular action, you have like a 10% chance of failure. Then you need to replan again. I mean, I think that could be put in the knowledge graph as well. Like sometimes you go to failure, but the way you traverse it might be different because you cannot just do a deterministic traversal. You could. It's just that when you do that particular action, you may not succeed. Right? So I think that is a tough problem to do. Right? Or what I was thinking of is maybe in this knowledge graph architecture, it could be more high-level actions that will always work. Like you just assume that after you cook the sausage, you always cook. So at a low level, if it's not cooked, you have a low-level planning mechanism to redo that part. So it's robust. But at the high level, it could be stored like this, like what you're doing right now. Yeah, so that's at least one way I was thinking of. Yeah.
Yeah, the main idea for the TextWorld environment was, as you said, the model, the higher level decision making for the stuff, and yeah, the details in you failing to do stuff, not like even overcooking the sausage, but like moving the robotic hand slightly several degrees in the wrong direction. That's not what language models are good at. So this should be carried by some maybe RL stuff or some planners and rule-based stuff. Yeah.
All right.
Well, the different problem is for the knowledge graph and for our example is if we move to the different environment with the same knowledge graph, we have a different red pepper and we have different recipe and so on. So how do we update our existing memories without erasing it, just to apply to the new environment? Do we create a separate knowledge graph and connect it as a like hyper nodes with for each graph for different environments and so on? So all these problems here also need to be addressed.
You raise a relevant point here, like the knowledge graph itself, the schema might also be constraining in terms of what you can extract out, like what nodes and what relations. So this may not work for arbitrary environments. You might need like separate knowledge graph for different environments, or you might need a way to represent things in a more abstract way and also more specific way. So there could be different forms of knowledge graph and so on. Yeah. I mean, I think these are interesting questions to think about for the future. In fact, knowledge graph might not be the only way to store stuff. You might also store stuff in different forms of memory that have not been invented yet. Yeah. So
Yeah, sure. Now, well, our basic idea why we like the knowledge graph, it can serve like as a backbone for the memory. Like the idea is, well, not like the knowledge graph is the best thing ever. And the idea is just you need to connect the different memories in different parts. And as you said, we can store memories in different formats, but we need to be able to connect them. The knowledge graph just seems to work for this stuff, this purpose.
very nice. So well, overall, I talk about a lot of improvements and so on. I think this work is quite impressive. Like it has solved a lot of difficult environments, and trust me, it's quite difficult. And this is really a very big improvement over prior methods in just the way we constrain the agent's inputs using smart extraction using knowledge graph. And also in the way that we like let the agent do planning in a chain of thought manner and so on. So I really think there's a lot of promise in refining the kind of memory spaces that we use to solve problems and refining how we do the planning. Like the one that you found out, like you should separate the planner and the executor. I also found something similar when I was doing task gen. Like it really makes the whole sequence more effective. Yeah, we need to find out more of such things and integrate them into one coherent structure. Yeah, so on that note, I'll pass the time to Peter, Nikita. You have any last concluding words you want to tell everyone before we end today?
Well, I think we talked about everything interesting. Thank you, John, for the great discussion and for the opportunity to present our work. I think the task gen is also very impressive, and I wish you all the best in the development of this framework. And I think we will maybe look into this too to maybe implement some of our stuff if it will work.
Yeah.
Nikita, you have anything else to add?
Uh, it's interesting question. I I don't really understand what you say. Sorry.
Yeah. Do you want to add something in the end? Что-нибудь добавить хочешь еще в конце?
I don't know.
Well, okay.
The-
I think
Sorry.
we covered all the important stuff.
All right. All right. So I think that's a great note to end. I hope that this AriGraph can continue to like incorporate new elements and improve to solve more arbitrary environments. It'll be very interesting to see how it works out in the future. And yeah, so yeah, thanks all for presenting, and I'll be ending the session. Yeah. See ya.